In this video, we're going to take a look at the dot product as well as the cross product of two vectors. So for our first example, let's take a couple of vectors in the plane. Vector A looks like 4i plus 3j, and vector B looks like minus 6i plus 5j. So for part A, we're going to find the dot product of these two vectors, so A dot B. First important thing to realize here is that dot product is a number. So when we calculate A dot B, we're doing a little bit of arithmetic here. The rule is you take the x components of the two vectors, multiply them together. So we go 4 times negative 6, and then we're going to add on the product of the y components. So we'll add on the product 3 times 5. So a dot product is just a sum, and each term is a product. So we've got minus 24 plus 15. That gives us negative 9. That's our dot product done. So one of the nice applications of the dot product is finding the angle between a couple of vectors. So let's find the angle between our two vectors here, so between A and B. So to do this, we need another way of thinking about the dot product. A dot B is equal to the magnitude of A, or the length of A, times the magnitude of B, times cos theta. And theta here represents the angle between our two vectors. Now in this setting here, the angle between two vectors is always somewhere between 0 degrees and 180 degrees. So we never talk about angles that are bigger than 180. We can probably visualize that best just using a little picture here. So imagine that, say, one of our vectors is going over like this. Maybe we have another vector going over like this. So it doesn't really matter here which one's A and which one's B. The idea is that when we talk about the angle between the two vectors, we're always talking about the smaller angle. So we never need to use an angle bigger than 180. If that happened, we'd just choose the angle going in the other direction between the two vectors. So we'll always be able to get an answer somewhere in between 0 and 180 degrees. All right, well, let's try it for these particular vectors here. We've already calculated A dot B in part A, so let's work on finding the magnitudes of our two vectors. Well, magnitude of A, we're going to do the square root of 4 squared plus 3 squared. If you forget exactly why this formula works, you may want to go back and look at our previous video on vectors where we calculated the magnitude. But that's our general formula for magnitude for vectors in the plane. Okay, so that works out to 5. Vector A has length 5. And vector B, to get its magnitude, we're going to go square root of negative 6 squared plus 5 squared. This one doesn't work out to a particularly nice number, so we'll just leave it as square root of 61. So there's the length of B. Okay, now we've got everything we need to plug into our formula. So I'm just going to write out this formula again. It's good practice. Formula that we should be familiar with. A dot B is the same thing as the product of the two lengths times cos theta. So now it's a little bit easier to visualize plugging in. We said that our dot product was negative 9. And our magnitudes were 5 and root 61, so that all gets multiplied together, and that's still times cos theta. All right, so with a little bit of rearranging here, cos theta is equal to negative 9 divided by 5 root 61. And to get our angle here, we can bring in arc cos. So arc cos is going to come in and just undo the cosine here. We'll have arc cos of -9 divided by 5 root 61. Now, in doing this calculation on your calculator, one problem that people often run into is just an order of operations issue here. So for the purpose of using your calculator, you might find it handy just to put brackets around that entire denominator. That way the calculator understands it has to divide by the entire quantity, 5 root 61. If you don't do that, you may end up with some kind of something strange going on here. So let's grab our calculators and check that we come up with theta approximately 103.3 degrees. So there's our final answer there. Next, we'll do a little bit of practice with the cross product. So let's take a vector A in 3 dimensions. A looks like 3i minus 2j plus k. And vector B, also in 3 dimensions, looks like 4i plus 6j minus k. So for this problem here, we'd like to practice finding the cross product of these 2 vectors. So the important thing to keep in mind here is that the cross product is a vector. So our final answer should look like a vector in 3D. It should have the same form as our vectors A and B that were given in this question here. So here's how I like to think about the cross product. I'm going to write down vectors I, j, and k. Underneath this row, I'm going to write out the components of the vector A. So 3, -2, and 1. And underneath that, I'm going to write out the components B, 4, 6, minus 1. Okay, then beside this, I'm just going to recopy the first 2 columns. So the first column looks like I, 3, 4. We'll just recopy that. And we'll recopy the second column as well. So J, -2, 6. Okay, now what we're going to do here is form a bunch of products. So we're going to take products in this positive direction here, just going from the upper left down to the bottom right. So that will be one product. There's another one, and there's a third product. So now you can hopefully see why we had to recopy the first 2 columns there, just to make sure that we had enough numbers to fill in this little diagram here. Okay, we're also going to calculate some backwards products. So the backwards direction is when you're going from sort of the upper right to the lower left. That's considered the backwards direction. And each of these products is going to get multiplied by a -1. In other words, it's going to change sign when we write down our answer. So multiplied by -1, multiplied by -1. Okay, so forward direction is from the upper left to the bottom right. The backwards direction gets its sign changed when we write down our product. Now, A cross B is just going to be the sum of these 6 products. So hopefully we can read this, make out the numbers through the crossed out numbers. Our first product looks like 2i, because we got I times -2 times -1. So if we multiply all those things together, we get 2i. Okay, then we're going to go plus our next product. We've got a 4j. If we multiply these 3 numbers together. And then multiplying k times 3 times 6, we get 18k. So we'll add that on as well. Okay, now looking at our backwards product, we've got a 4 times a -2 times a k times a -1. So that gives us an 8k. So we'll add that on as well. Next backwards product, we got 6 times 1 times I times a negative 1. So that gives us a minus 6I. So we'll add that on. And then our last backwards product, minus 1 times 3 times j times minus 1. So that gives us a plus 3j. All right, so final step for calculating the cross product, we just need to collect like terms. So we've got a couple of i's, minus 4i. J's, we've got 7 of those, so plus 7j. And then for k's, we got 26 of them. 26k. Perfect. So there is our cross product. It looks like a vector and it's given in our I, j, k form, just like in the original question. So probably the trickiest part of doing the cross product calculation is just remembering which direction is the backwards direction. So usually when we're reading, naturally we sort of start reading something in the upper left corner. If you're going down this way, that's the positive direction. The backwards direction is this sort of more awkward diagonal that we're drawing in that other direction. Okay, well, let's talk for a minute about why the cross product is useful to us. Very useful in physics and in engineering because A cross B, a cross product of two vectors, gives us a vector that is perpendicular to the original two vectors that we started with. So our cross product is perpendicular to both vector A and vector B. So if we were just to draw a generic picture here of any two old vectors here, let's say that's A and that's B, the cross product then, because remember we're working in 3D here, the cross product is a vector that's perpendicular to these two. So A cross B would be looking like this. It's going to be perpendicular to A, and because we're in 3D here, it's also possible for it to be perpendicular to the vector B at the same time. Okay, so imagine A and B are lying in a plane. A cross B is a vector that's coming straight up out of that plane. Now, it turns out that if you were to calculate B cross A, if you did the calculation in the other order, you would actually get a vector that's pointing in the exact opposite direction. So for that reason, it's important that you write down your vectors here in the correct order. Notice that we put A first, and then we put B. So if you had reversed those, you can check, you'd have the opposite signs coming out in your components there. So you want to just be careful about the order. Now, one last comment here. In this picture, we need to think about how we really know that A cross B is pointing up and B cross A is pointing down. Well, this fact comes from something called the right-hand rule. Okay, so there's a bunch of different formulations of the right-hand rule, but the way I like to think of it is if I line up my pinky with the vector A, so line up my pinky so it's pointing in the same direction as A, and I let my fingers curl towards B, then my thumb is roughly going up in the direction of A cross B. So if I line up my pinky with A, let my fingers curl towards B, my thumb's being pulled upwards as that happens, and that says A cross B is pointing up, B cross A is going to be pointing down.